Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session on phase detectors. So, earlier we have looked at analog phase error detectors, okay, and out of those analog phase error detectors we looked at two in particular. First one was mixer or multiplier based PD, and the other one was your sample and hold. Okay. So, one of the things which we found in these cases that the mixer output was non-linear, okay. Sample and hold PD. Now, we are going to look at digital phase error detectors, and when I say digital phase error detectors, well, these phase error detectors are going to operate on digital signals, or you can say CMOS signals which have two output levels 0 and 1, okay, logic level 0 and 1. So, the first one here is exclusive OR based PD, which is also called as EXOR based phase detector. Okay. So, this is exclusive OR based PD. Now, let me first talk about what do we mean by phase error when we are having two square wave signals. This is something which we also saw yesterday. So, if you have two clock waveforms which look like this, which are square waves. Okay. So, this is R waveform, and then let us say I have V waveform, where both of them have same output levels as shown to you here, and the rising edges of the two clocks, this is R, this is the rising edge, the rising edges of the two clock that differ by some value, let us call this as delta T1 and this one as delta T2. Okay. If the time period of both the clocks is going to be same, then the phase error delta T1 or the timing error right now, which you see delta T1 and delta T2, that is going to be same. So, this is the time period, this is delta T2. So, here couple of things which we need to understand, that phase error is always measured with respect to a reference. Phase error is measured with respect to a reference clock. Okay. And in our case, that reference clock is here, the reference clock is R. Why it is important to say that? Because phase is a dimensionless quantity, and in order to define the phase you need to know the time period. So, the time period which I am going to use is for the R clock. Here the reference clock is R with time period T. It may happen that the clock V may or may not have the same time period as V. Okay. So, for reference R, I can write F reference as 1 over T. Now, the phase error here is defined as the error between the timing error between the rising edges of the two clocks. So, what is the error here? At, let us say, you start with time instant t equal to 0. So, this is t equal to 0 with respect to time. So, what you see here is the error between these two rising edges is delta t. The phase error will be defined as 2 pi times delta t by t. Okay. If the two clocks are if the two clocks have the same frequency, then this delta t will remain same at every rising edge of r. So, here also delta t, here also delta t, all these timing errors are going to be same. So, when we are detecting the phase error for square wave signals using some circuit, at that particular time we want the output of the phase error detector to be proportional to this delta t. Okay. So, now what is this exclusive OR gate? You have an XOR gate, is as simple as that, and the output of the XOR gate is the output of the phase error detector VPD. This is R and V. Now, you will remember how simple it is, right. So, here at both the rising edges, we are going to see VPD like this. So, when you have one is logic high, other is logic low, your output logic will be high here. Okay. When both the logics are high, at that time the output will be low. Deliberately I am showing you signal like this, like it has the XOR gate. In this particular example, you can say the high value of the XOR gate is V and the low value of the XOR gate is minus V. Okay. You can have V and 0 also, that is not a problem. In order to avoid any confusion with the signal V, I will avoid this V here, I will use this as A and minus A. VPD output. You can very well have A and 0. In just for this case of for this analysis, you will find it is quite easy to look at with A and minus A. Okay. Then you see that okay, again there is a change of sign, change of output. So, this is A and then this is again going to be 0 here, and this will repeat if you are having same frequency. Okay. So, interestingly what you see here is if both R and V are having same signal, then this delta t is going to be same for both the for all the clock periods. And the interesting part here is that this pulse actually repeats after every t by 2. So, this time period is t and this is t by the other one is t by 2. I can assume that this is t by 2 if I say that the duty cycle of the clock is 50%. Okay. Now, for this particular XOR gate, you see that the VPD is having a waveform like a pulse kind of waveform, okay, and it is changing at the rate of your reference. So, here we define the average value of VPD for the reasons which we discussed earlier. So, average value of VPD is equal to A times delta t, okay, minus t A times t by 2 minus delta t, and this average value is taken over t by 2. You want, you can take it over t also, just that you will have to entertain this pulse also. Since it is periodic, whether I take an average over t or I take an average over t by 2, they both are going to be same. So, now this tells us that this is equal to 2 times delta t minus t by 2 whole divided by t by 2. So, you can take t by 2 inside. Okay. So, as you take t by 2 inside, what you get here is 4 times, sorry, this is delta t, 4 times delta t divided by t minus 1. Now, in this case, I will just change from delta t to phase error using the relationship as given here. So, this can be written as delta t by t is nothing but 4 into phase error by 2 pi minus 1. This is equal to a times 2 times phase error by pi minus 1. Okay. So, for the XOR based phase error detector, what you see is VPD average is a times 2 into phase error by pi minus 1. Okay. Let us just plot this. So, here I am going to plot the average of the phase error detector output with respect to phase error. So, when phase error is equal to 0, at that time you will have value of minus a, okay, and when phase error is equal to pi, at that time you will have plus a, okay, and then in between you will go from minus a to plus a. Okay. This is pi and this is pi by 2. And this particular phase error, as you move to, as your phase error increases more than pi, you will see it will go like this. Okay, sorry, it will cannot exceed minus a, and this will continue. On the opposite side, or you can say for the negative phase error, what happens is that you are going to see like this. This is going to be minus pi by 2 and this will be minus pi. Okay. So, now if you look at this phase error detector characteristic, the average value of the phase error detector average value of the phase error detector is showing you a linear response from phase error of 0 to pi, right. If you talk about XOR gate independently, the XOR gate independently is non-linear, right. It has only 2 levels, output levels. In terms of voltages, it is non-linear. But if you are using in the manner as I have shown here, then you see that the phase error detector, this particular phase error detector behaves much more behaves in a linear fashion in the range 0 to pi. Okay. If I am going to add this particular phase error detector in the PLL, just for an example, you take this phase error detector, you feed both your reference and the output signal with loop filter and VCO. Then in that particular case, you will see this is your VPD output. Okay. If your loop filter happens to be, a type 2, you will lock to average value of phase error detector as 0, because for type 2 loop filter you have an integrator, you have to have in the locked state the average phase error detector value is 0, which means your locking point is going to be phase error of pi by 2. Locking to a phase error is not a problem in PLL. The only thing is, if the PLL is locked, the phase error should not change with respect to time, that is important. Okay. So, what you see is that this particular phase error, it behaves linearly here. So, quite often we use a change in variable here, where we just shift this plot, and in place of having our axis at phase error of 0, I change the variable, and now I have this as VPD average, and This is the change in the variable. Now, it is no more called as phase error, but is phase error S, shifted one. What is the importance of this? Well, okay. So, here what I have done here is the phase error pi by 2 will effectively become 0. So, I need to change this. Oh, yeah, this is 0 here, this is plus pi by 2 and this one is minus pi by 2. I am just changing my axis and this becomes minus pi, this is minus 3 pi by 2 and so on. Okay. So, the change in variable which you are looking here is previously your whatever was pi by 2 that now has become 0. So, the change on the variable which I am using is phase error in steady state or phase error shifted is equal to phase error, right, minus pi by 2. This is the change in the variable I applied and then I plotted V P D average with respect to phase error S. So, what you see here is that your pi by 2 translates to 0 and pi translates to pi and this one translates to this point. Well, other than ease of looking at this phase error detector, there is nothing much which we did. So, coming back to phase error detector output, what we see here is that XOR based phase error detector is linear, is actually linear, is not only monotonous, it is linear in range plus minus pi by 2. In contrast to your mixer based and your sample and hold based, the range is actually perfectly linear. The gain of the phase error detector, okay, which is KPD. Now, this is just like finding a slope of the line, which is not any different. So, slope of the line is from minus pi by 2 to plus pi by 2 is 2 times A, right, divided by pi. So, whatever your amplitude has, that amplitude gets multiplied. Okay. So, this is volt per radian. So, the things which we look for is the linear range, the gain of the phase error detector, right, and on both the counts what you see here is the gain is constant throughout this range, right. The gain is constant, the gain is you have a linear range. So, this appears to be much better than the phase error, the mixer based phase error detector where you have seen the gain is constant, right here. So, in contrast to your mixer based stuff, in mixer base you had gain as non-linear, okay, and there was no linear range, there was like a monotonous range which we had. But here we have on both the counts you actually perform better. Now, given this phase error detector and our analysis, actually when you go and implement, there is some inherent problem to this phase error detector. So, let us just look at it. So, what happens if our clock has a duty cycle error? So, let us say the reference clock is pretty good, reference clock has no issues. The problem is actually with the V clock which is generated by the oscillator. So, if that is the case, I will just show you one case where I have a duty cycle error. I am plotting a modified V and this modified V happens to be some value like this. Okay. So, in place of having the high time of t by 2, it has a high time of t h. I will just write this with V dash. What happens if you have high time of V h? Well, the output which you see here is the actual phase error is between these rising edges which still remains t, but what you are going to see at the output of the phase error detector, this is fine, and then depending on your duty cycle of the clock, you will get high for so here now you see this is high and this is low. So, you are going to get high for this region. Okay. So, I am plotting this for V dash, this is V P D dash. When I am plotting on the same curve, it may be easier for you to recognize. Okay. So, this is the duty cycle error which you see. What is duty cycle? Duty cycle of the clock is defined as D is equal to T H divided by total time period. Okay. Now, if the phase error changes, for example, phase error changes by a small amount here, let us say, and the duty cycle remain the same. So, what do you see? The output will be like this. It's now it is going to be periodic in T rather than T by 2. So, I have shown you another waveform with V double dash, let us call that. Okay. In response to V double dash, you are going to see your VPD double dash like this. Okay. Yeah, right. So, the interesting part here is even when the phase error changed from blue to the red one, the separation between the rising edge of the reference clock and the rising edge of the V clock, if that even when that happens, what you see is that the total area which was earlier for the blue one was this. Okay, this was the total area earlier, and the area when it changes to the red one to yellow, you add this green here, and on the other side you deduct this green. Okay. What you will find here is that the total area for which the clock is high is still remains the same. It very much depends on the phase error. Okay. So, for two cases what I have discussed here. So, the one for V P D double dash. Okay. So, the point is the following: in the presence of phase error, we will calculate the equation with equations later, but just first understand what is happening. In the presence of phase error, I am going to write 2 pi times delta T 1 by T, right. Your V P D dash, the average of the V P D dash is same as average of V P D double dash. So, here actually you have two phase error. So, in the presence of phase error 1, phi error dash equal to 2 pi times delta T 1 by T, and phase error double dash, which is, do not think this double dash as a derivative, this I am just using for different sign, delta 2 by T. What you have is VPD average, VPD dash average is same as VPD average, and this you can easily relate by looking at the area under the curve when the clock, when the output is high and when the output is low. Okay. So, this is going to happen. It will change when the phase error exceeds such that your high time actually crosses this. That time it will change. Till the time it remains within the T by 2 some region, it is going to be same. So, just another visualization for that. So, this is our high time for our clock. Okay. So, whether, so I will plot multiple. So, if you have something like this, okay, this is your TH, this is the total, you can say T by 2 minus TH. Whether you have V as this or you just shift the clock and have some phase error like this, or you have another one where you shift the clock, you have more phase error, it becomes like this. Okay. The area is going to be same for VPD dash, VPD, right. It is going to change only when you can say after a point where it becomes like this. If the phase error exceeds from this value, what is this value? Well, this value is nothing but T by 2 minus TH. If the phase error exceeds this value, then only you are going to see a change in VPD output. So, based on this, we can actually plot the average of the phase error detector, and the average of the phase error detector happens to be. So, if I call, let us say this is minus A and this happens to be A, right. This is phase error, this is VPD average. So, this is going to be constant for some time and then it will change, okay, and it is again going to be constant on the other side for a while. Okay. This value is going to be, it is not going to cross 0 at pi by 2, at pi by 2 it is going to be some other value. By the way, this is pi. As the phase error exceeds pi, you will again see the constant part, right. This value happens to be minus 2 times d times A, and on the positive side this is 2 times d times A, right, and this phase error is, sorry, this offset point is actually pi times 1 minus 2 t. Okay. So, what you see here is that in place of VPD average reaching minus A and plus A, right, it gets fixed at two different points, which is minus 2 d A and plus 2 d A. Okay. Interestingly, the gain, the linear gain during this region, or the gain, not the linear gain, the gain during this region still remains the same as what you have previously. What was the gain? 2A by pi, this still remains 2A by pi radians per volt. It is very simple, this is pi, right. So, I can just, from here I can just calculate, that is like 4 d times A is the output, divide by 2 pi d. So, dd goes off, you have 2A by pi. So, gain remains the same, the linear range actually reduces. Now, the linear range is going from pi of minus 2d to pi, that is our range. Okay. You can again shift this plot back to this plot wherever you find that the phase error is equal to 0. Okay. During this time, you have the phase error equation given by, I will write it, you can also calculate it for delta t error, which is greater than 0 and less than actually equal to t by 2 minus d times t. Okay. D is actually your duty cycle, which is Th by t. For the phase error less than this, you have your VPD average given by minus 2 times d v, sorry, d a here. Okay. For phase error greater than, I am writing in terms of timing error, but I am calling this as a phase error because timing error is directly related to the phase error. For this delta t less than equal to t by 2, your VPD average is actually equal to minus 2a times 1 minus d minus 2 delta t by t. You can substitute in this equation and you will find the values accordingly. Okay. So, your phase error detector will not lock to pi by, your PLL is not going to lock to pi by 2, but it is going to lock, if the frequencies are same, PLL will lock for VPD average equal to 0, right, which implies if VPD average is equal to 0, you can just substitute it back. What you see here is 1 minus t minus 2 times delta t by t is equal to 0, which is like delta t is equal to t by 2 into 1 minus t. Okay. If you want to do a sanity check, in previous case earlier, our d was actually half, duty cycle was 50%, right, which implies delta t is equal to t by 2, 1 minus half, this is t by 4. Well, t by 4 translate to phase error of pi by 2, right, that this was the locking point earlier, and now the locking point has just shifted, but that is fine. So, because of the duty cycle, we have a problem that the phase error is not linear throughout the range 0 to pi, okay, or earlier like minus pi by 2 to plus pi by 2, that range has reduced. Okay. But what has happened is the range has reduced, but the gain remains the same, okay, and the gain is constant in that range or in the reduced range. Okay.